with the structural properties, structural descriptors, structural features. Okay, that is why we call it quantitative structure activity relationship. We will talk about what are those structural descriptors, structural features and so on, okay, later as we go along. So you get a mathematical relation, that is why you say call it a quantitative structure activity relation. Chemists have been using SAR for a long time, that is structure activity relationship for a long time. If electron donating, you may have activity, electron withdrawing less activity, or hydrogen bond forming more activity and so on. Alpha beta unsaturated may give more activity. So that is a structure activity relation. So they used to synthesize molecules with different features and see how the activity changes. From there they develop a understanding, that is an understanding, that is why it is called structure activity relation. Whereas in computational work we bring a quantitative aspect to that, that is why we call it a quantitative structure activity relationship here. Okay, let us look at these in very detail. This is widely used for ligand based drug design, especially when we do not have any idea about the target. We know certain molecules give activity, certain do not give. So we find out what are the structural features which give and then try to find out whether we can develop a mathematical relation. Okay, so it is a mathematical relation between the biological activity, that is the experimental value. That means that is very important. We need to have experimental data a priori of a molecular system and its geometric, physical, electronic, chemical properties, large number of properties. Okay. So we try to get a mathematical relation. Can be used to predict activity of unknown new compounds. So what it means is, okay, suppose I developed a QSAR. Now I have an unknown new molecule. My medicinal chemist says, can't we synthesize this molecule, a new structure. So I can try to predict activity of this new structure, that is the unknown. Before going to my lab, I can predict what will be the activity. That is why QSAR is very important. Okay. Another advantage, okay, suppose I have a large pool of molecules, instead of spending a lot of time going to my wet lab and checking their activity over a long period of time, I can predict the activity of these molecules using the QSAR and then sort of grade them or categorize them as those which will have good activity and those which might not have, and then select those maybe top 10 or top 15 which may have good activity and then take it to my wet lab. So that way I can shortlist, basically I can shortlist my molecules. If I have a large pool, instead of taking all of them into my wet lab and performing experiments which may be very time consuming, I may take the top 10 or top 15 which using the QSAR may have good activity. So this is the advantage of QSAR. So I start with the known structures whose experimental activities are known, okay. Then I develop a QSAR. So with that QSAR I can do two things. I can predict activity of a new molecule before going into my wet lab. If a medicinal chemist says why not this structure, immediately with the QSAR I can predict of unknown molecules. And if I have hundreds of molecules or thousands of molecules, instead of taking all of them into my wet lab and then checking out the biological activity which could be very time consuming, I may predict the activity of these hundreds or thousands of them and then put them in the descending order and take the top 10%, top 20%, take it to my wet lab and check it out for their biological activity. So that way I can shortlist, okay, that saves me a lot of time instead of taking in the entire thousands of molecules. So QSAR is useful in that way also. Okay. So basically you develop a mathematical relation, left hand side you have the activity, right hand side we will have some function of property 1, property 2, like it could be size of the molecule, shape of the molecule, number of hydrogen bond donating groups, number of hydrogen bond forming groups, electrostatic, so many things. We will look at them more in detail. These are called the properties of the molecule. Okay. So we can have QSAR, quantitative structure activity relationship. Nowadays quantitative structure property relationships have come. That means I can predict properties like for example log P. If you want to predict log P for new molecules, how do the softwares do? They have QSPRs. So they can predict the property or the log P of a new molecule from known molecules. They would have developed a mathematical relationship. Solubility, there are many QSPRs for solubility from known molecules. They predict the they develop a QSPR, and if you input unknown structure, for example in Swiss ADME, it calculates the solubility of that molecule using QSPR. Similarly QSTR, quantitative structure toxicity relationship. So if you have toxicity data of some molecules, you develop a mathematical relation QSTR. So if you input a new molecule, it will predict what is the toxicity of that molecule. Okay. So nowadays QSARs, QSPRs, QSTRs are very common. Some of the softwares I showed you, there are many software which has this QSPR, QSTR inbuilt in them for predicting properties like solubility, log P, and then toxicity values, different types of toxicity values given the structure. Okay, basically, so on the right hand side we have the various properties, okay, like I said, size, shape, number of carbon atoms, all these are properties. Okay. So the QSAR is a quantitative relationship, do not forget that. It is not a qualitative but a quantitative mathematical relation. That is why we say quantitative structure activity relationship. Okay. Now these properties or structural features, they are also called descriptors. These properties of molecules or features, they are also called descriptors, physicochemical properties. Okay. Like I said, shape, size, they are physicochemical. Electronic property, okay, so charge on the molecule, or largest, highest negative charge, highest positive charge. Steric factors, okay, the shape gives you the steric factor. Lipophilicity, the log P value, the polar, those are all lipophilic. Hydrogen bond forming, that means hydrogen bond forming, hydrogen bond donating, hydrogen bond accepting, shape of the molecule, charge distribution on the molecule, polarizability. So all these are different types of structural properties or features or descriptors. So they are all used in QSAR. Structural descriptors we say structural properties, structural features, all these are various types of numericals which we can estimate for a given structure. So if I draw a structure, we can calculate these descriptors. Nowadays there are softwares which can calculate thousands of descriptors, almost 2500 descriptors. We will look at some of those softwares as we go along. There are many web based softwares, downloadable softwares which can calculate descriptors for any given structures. Okay. And then with those descriptors we try to select the best descriptors and then try to develop a mathematical relation between the activity on one side, that is the left hand side, versus the function of descriptors. Okay, 1 descriptor, 2, so on. So obviously we need to have a large number of data points if we want to have many descriptors in the model. Okay, that is statistics. Okay, if you have done a course on statistics, you will know how many descriptors we should have for activity. Okay, let us look at some simple system. Okay, imagine I want to have a good basketball team, so I am selecting basketball players for my team from the college. One approach is to make all of them play and then select the team. That is going to be very time consuming. Imagine a college with 8000 students, that will be very time consuming. So I may look at some features of the people, right. Based on these features I may shortlist a group, and then that group I may test it out to see whether they play well. Okay, that is the best way to do, instead of making entire 2000 people to play basketball, which is going to be very time consuming. Okay, so what are these features? Height, for example, ideally we would like to have tall guys. guys with long limbs, long hands, long legs, strong legs. They should have strong legs because they should be able to run around and all that. Focused, okay, deliberate, full of fire, range of motion, agility, long training, strength, speed, endurance, passion, all these make a good basketball player. See, but then some of them are quantifiable, some of them are not quantifiable. Okay, say height means I can tell he is 200 centimeters square. Okay, long limbs I can tell the hands are so many centimeters, legs are so many centimeters, whereas things like deliberate, full of fire, these cannot be quantifiable. For QSAR we need to have only quantifiable descriptors, that is very important. So we need to look at only quantifiable descriptors. Speed, maybe I can make them run 100 meters and then find out how many seconds they take, and I may say okay, people who take less than 11 seconds 100 meters can be considered as the team. People around 180 centimeters can be taken height, and so on. So I can select some of these as my descriptors. So from 2000 students I may select maybe 100 students who have a certain cutoff on height, limbs, speed and so on, and then I may see whether they play, take them to the court and make them play and see whether they are able to play. Okay. So these could be the descriptors or features, structural features for selecting a good basketball team, and that is what we do in our drug discovery. So we know lot of descriptors for a molecule, electronic descriptors, shape descriptors, size descriptors, thermodynamic descriptors so on, and then I develop a mathematical relation between some of these descriptors with their activity, so that I will have a QSAR. Okay, there are some problems in this. Okay, for a basketball team, or if you are talking about a athletic team, sports team, I can look at height, limbs, speed, all those things, right. But then look at it, I want to select there are 2000 students, I want to select students whom I think have high IQ. One thing is I can make them do an exam test, conduct an IQ test for a couple of hours or 3 hours, and then take those who have 120 above. Instead of that, from their structural features can I shortlist? It is not so easy. Can height be a feature representing IQ? No, it might not be, right. It need not be that tall people will have IQ or vice versa. Can limbs be? So there are many descriptors which need not be a representation of the IQ. Maybe big brain, maybe size of the brain, maybe okay, maybe the weight of the brain or size of the brain may be a representation of the IQ, but look at this, there are problems, right. We do not know which descriptors will predict their IQ. So in QSAR that type of problem can also happen. We do not know which descriptors to select to predict the activity. Okay. Sometimes we can predict, for example, if you are looking at antioxidants, we may say a phenolic group or OH type of group may lead to good antioxidant property. Similarly, antibacterial, we may look at molecules which may have alpha beta unsaturated or which may form quickly radicals and so on, but it is not so easy to say which descriptors are needed to predict a particular activity. So that problem can happen like this, I do not know which descriptors to select to predict the IQ. So if I take height as a predictor of IQ, that is wrong. Long limbs, that also could be wrong. Whereas so see in this particular case you may be able to select descriptors to predict whether he will be a good basketball player or a good athlete or a good sportsman, but here it may be very difficult to find descriptors. So the same thing can happen when we are doing QSAR in drug discovery. So we may not have the correct descriptors to select, we may be selecting the wrong descriptors also. We are not sure what should be the descriptor for this IQ. So we may be selecting the wrong ones, so that is a danger that can happen in QSAR also. So that is a shortcoming in QSAR, we need to think of it. Okay, there are a lot of descriptors, like I said, molecular descriptors used in QSAR. For example, hydrophobic, electronic, steric. Hydrophobic, you can have log P, Hansch substitution constant. So, if you have CH3 groups, OCH3 groups, OH groups, some of them lead to lipophilicity, some of them lead to hydrophilicity, right. Hydrophobic fragmental constant, distribution constant, solubility, they all come under the hydrophobic. Electronic, Hammett constants, Taft's inductive polar constant, Swain and Lupton field parameters, ionization constant. Steric, Taft's steric parameters, molar volume, van der Waal radius, van der Waal volume, molar refractivity. So, you can have descriptors, you can have sub descriptors under each category also. So, you could have lot of descriptors. Like I said, we can have 2000 plus descriptors for given structure. There are softwares which can calculate them. Quantum chemical atomic net charge, super delocalizability, energy of highest occupied molecular orbital, energy of the lowest unoccupied molecular orbital. Then spatial descriptors, juice descriptors, shadow indices, radius of gyration, principal moment of inertia. So, large number of descriptors, see, hydrophobic related, electronic related, steric related, quantum chemical related, spatial related. Of course, we also have thermodynamics and all that also, like heat of formation, delta G, that sort of descriptors. So, large number of descriptors are possible. There are some 0 dimensional descriptors, 1 dimensional descriptors, 2 dimensional descriptors, 3 dimensional descriptors. Okay, let us look at it. Atom count, number of atoms the molecule has. Bond counts, number of bonds the molecule has. Molecular weight, what is a molecular weight? Because the molecular weight may have an effect. For example, as you know, large molecular weight diffusion may be a problem, small molecular weight diffusion is easy. Sum of atomic properties, chemical formula. So, molecular weight, average molecular weight, number of atoms, hydrogen atoms, carbon atoms, heteroatoms, these are all non-carbon and non-hydrogen atoms. Number of double bonds, as you know, double bonds, it is easy to oxidize or they are easily reactable. Triple bonds, aromatic bonds, because they form resonance, rotatable bonds, because as you know, rotatable bonds can change the conformation of the molecule so that it can go and fit into active sites. Rings, 3 membered rings, 4 membered, 5 membered, 6 membered, as you know, highly strained, 3 membered, 6 membered is very good. So, all these are possible structural features of a molecule. They are also called descriptors of the molecule, structural features, structural descriptors. So, they are called 0 dimensional descriptors, okay, 0 dimensional descriptors. Okay. Fragment count, okay, these are all 1 dimensional descriptors. Fragment count, number of primary carbon, secondary carbon, tertiary carbon, quaternary carbon, secondary carbon in ring, tertiary carbon in ring, quaternary carbon in ring, unsubstituted aromatic carbon. So many variations on carbons itself, number of hydrogen bond acceptors, unsaturation, they are all called 1 dimensional descriptor, okay, 1 dimensional descriptor. These are 0 dimensional, these are 1 dimensional. 2 dimensional, these are all 2 dimensional, as you know, is topology, okay. There are indices like Zagreb index, Wiener index, Vallabhan J index, connectivity indices, chi, kappa shape indices. So, they are all topology related, they are all 2 dimensional descriptors. So, when I draw a structure, so I can get all these, okay. Of course, then we have 3 dimensional, when it takes a conformation, and the geometric descriptors, radius of gyration, because that depends on the shape of the molecule, okay. 3 dimensional electronic state, topological parameters, 3 dimensional Wiener index, 3 dimensional Vallabhan index, surfaces, van der Waal surface area, solvent accessible surface area, polar surface area, isotropic surface area, non-specific interactions with the solvent, geometric, electrostatic, charged partial surface area, highest occupied molecular orbital energy, lowest unoccupied molecular orbital energies, energy difference between this HOMO and LUMO, active conformations, global minimum conformations, binding energies, ionization potentials. So, these are all 3 dimensional descriptors. So, as you can see, once I get the minimum energy confirmation, I can calculate all this. If I draw a structure using a structure draw program, I can calculate all this. Without drawing from the molecular formula, I can calculate these, and then once I do it by hand, I can calculate all these. So, these are some descriptors, and of course some I might have omitted. Like I said, there are softwares like eDragon which can calculate 2000 plus descriptors for performing QSAR. So, large number of descriptors can be estimated given a structure. Okay. Global descriptors log P, okay. Log P, once I know the molecular formula, I can calculate the log P using a QSPR volume, surface area, polar surface area, non-polar surface, dipole moment, refractive index. Then local descriptors describes a part of the molecule, okay, charge in one portion, hydrogen bond donors and acceptors, partial volumes, alignment, then you have alignment dependent descriptors, okay, when it is aligned, those descriptors, these are all called global descriptors. Okay, so there are many methods to develop the QSAR relationship, that is quantitative structure activity relationship, free energy models, mathematical models, statistical methods, pattern recognition, topological methods, quantum mechanical methods, and so on. So, large different types of approaches. We are going to look at many of them in the course of this topic QSAR. So, many different approaches are there, most, and as I said, they are all mathematical relationship because it is a quantitative structure activity relationship. So, they are all mathematical relationship. Okay, Hansch analysis, this came into in the 1969, this is called Hansch analysis. So, log 1 by C, that is we have the logarithm, that is the PIC 50 for example, is equal to, you can have A constant log P plus B, sigma could be electronic, C ES steric plus D could be a constant, or you could have square and so on actually. So, it is a non-linear. So, you could have a linear relation. So, it basically has 3 terms, one related to the hydrophobic hydrophilic nature, one relates to electronic, one relates to steric. So, according to Hansch, any molecule QSAR could be defined using 3 basic things, okay. The activity will be a function of hydrophobic hydrophilic nature, log P, electronic, steric, okay, that is what Hansch said actually. Then we have free Wilson approach, activity is equal to summation of AI xi plus mu, mu is the overall activity, AI is the contribution of each structural feature, okay. So, if I have a structural feature like OH, then that will contribute to the overall activity. If I do not have, then that will become 0, okay. If I have, that will become 1. So, each one will contribute to the activity, either some of them may be enhancing activity or some of them may be pulling down the activity or reducing the activity, that is called the free Wilson approach, okay. So, remember Hansch analysis, free Wilson approach. Hansch analysis, they assumed hydrophobic hydrophilic contribution, electronic contribution, that is here, this is the steric contribution, that is here. So, linear relation will be of this form, okay. Some important points we need to consider. So, when we use 2 or more descriptors in my equation, and if 2 descriptors are highly related with each other, covariant, then the second descriptor isn't significantly changing the QSAR. So, we need to remove that, okay. So, if 2 descriptors, or for example molecular weight and volume, we cannot take this as descriptor 1, descriptor 2, because there could be a very good relationship between molecular weight and volume. If the molecular weight increases, volume increases. So, there is a relationship, they are okay, correlated, person's height and weight. So, mostly a tall person will be heavier than a short person who will be lighter. So, they may be interrelated. So, do not take a equation which has both height and weight as two independent variable. Okay, what is independent variable? When we say y is equal to a plus b x1 so when we write y is equal to a plus b x1 plus c x2, these are called independent variables and y is called the dependent variable. Okay. So, basically all these x's, that means the independent variables, should be independent of each other, they should not be correlated with each other, that is very important. That is what is called a multicollinearity. So, person's height and weight, for example, age and sale price of a car. So, older the car, sale price will be less, younger the car, sale price will be high. So, these two descriptors or parameters are interrelated. So, do not have a model which includes both as independent variable. So, year of education and annual salary, for example, if you have studied longer, your salary may be more. So, these two variables could be interrelated with each other. Okay. So, like molecular weight and volume. So, you need to keep in mind that when you have x1, x2, x3, x4 as independent variable descriptors, they should not be interrelated or correlated with each other, that is very important. Okay, let us look at some simple structure activity relation. Look at this molecule. Okay, these are called substituted benzoic acid, benzene ring COOH, R could be any group like this in ortho or meta or para. So, they are benzoic acid substituted. Now, they dissociate, okay, to form COO minus. Okay. The dissociation constant is given in this table at 25 degrees centigrade. Depending upon the substitution and depending upon the position, you can see the dissociation constants. You can see the numbers vary dramatically, quite a lot. It can be as small as say 4 or even 3.3, and it can be as large as 54.1. So, a fluorine in the ortho position can lead to a very large dissociation constant, whereas OCH3 in a para position here could lead to a very small dissociation constant. So, fluorine here does not makes it dissociate like this. Here OCH3 here pulls the electron, so it does not allow the dissociation taking place. Okay. So, this is a nice structure activity behavior. You can see depending upon the functional groups like nitro, chloro, fluoro, OCH3, CH3H. So, depending upon whether it is electron donating or withdrawing and in the position, that is the ease with it the electron donating or withdrawing can take place, the dissociation constant can change. Okay. And so, acid form is stabilized if R is electron donating, therefore, the equilibrium lies to the left. Okay. Acid form is stabilized, if it is like this instead of going like this. So, if R is electron donating, okay, R is electron donating. Okay, if R donates electron, acid form is stabilized. Anion form is stabilized if R is electron withdrawing, therefore, the equilibrium lies to the right. That means anion form that is on the right. Stabilized if R is electron withdrawing. Okay, look at this, electron withdrawing, these are all electron withdrawing, electron donating, OCH3 here. Okay. So, this is called the acid form, this is called the anion form. Acid form is stabilized if R is electron donating, anion form is stabilized if R is electron withdrawing. Okay. That means this form is stabilized if it is electron withdrawing, acid form is stabilized if it is electron donating. So, the increasing reactivity of this electron withdrawing, okay, these are all electron donating, OR, that is OCH3 OH, okay, increasing reactivity, So you can see down here, okay, and so on. So log Ka of the substituted acid minus log Pa of the unsubstituted, that means if you have H is equal to log Ka Rx divided by log of Ka Rx divided by Ka, and this is called the sigma. Okay. So larger the sigma, so there is a dissociation taking place. Why are we talking about it actually? Okay, let us talk about it. Why? Look at the antibacterial activity of sulfanilamines. These are called sulfanilamines. They are antibacterial. They are called sulfa drugs discovered after First World War. You can see the structure here. So there is a benzene ring S double bond O, S double bond O, NH. There is benzene ring with R. Okay. Antibacterial of sulfanilamines is due to their similarity to the natural metabolite para-aminobenzoic acid. They act in their anionic form. Only when they are anionic they act, when they are neutral they do not act. Okay. Why do they act? They look like the para-aminobenzoic acid, which is the natural substrate for the bacteria. So this sulfa drug goes and binds in a competitive fashion and does not permit the substrate food for the bacteria to bind, so the bacteria dies. Okay. So the anionic form is what is desired, whereas the this form is not desired. Okay. So R stabilizes the anion by electron withdrawal, thus increasing biological activity. Okay. So if sigma is larger, activity is also larger. If pK is larger, the activity goes down. So ideally we should have compounds, the R substitution, which makes it the anion form rather than the neutral form. So what is that? So we would like to have more of these type of molecules. Okay. So we will have more of these type of molecules. Okay. Anion form is stabilized if his R is electron withdrawing, therefore the equilibrium shifts to the light. Okay. So sigma is larger here, goes down. So that is a very important point we need to understand, how whether it is an electron withdrawing or electron donating, we end up either with the stable anion form or with a stable neutral form, and as I said, this is what gives the activity as an antibacterial drug. Okay. So depending upon whether it is electron withdrawing or donating, we have the proper anion form getting stabilized, okay, and hence improvement in the activity. Okay. So we will continue further in the next class on QSAR. Thank you very much for your time.